So we got 3.1 stats. And in 3.1, what we're going to be talking about is this thing called scatter plots. We're going to be talking some correlation. We're going to talk about least squares regression line. We're going to be doing some predictions. But all in all, we're doing a thing called bivariant data. Now, if you can break down those words, we got bi, meaning two, variant, variables. It looks like I wrote data. Bivariant, two variables. So let's do the first thing. I got a nice little data set here. Sometimes we do this in class, but we're not in class, so and not everybody has a Barbie doll. So let's just talk about it and what could happen. This is an old data set that we've had. Below is the data for one group's Barbie bungee. Essentially what we did was we'd take Barbie, right? If you know the Barbie doll, the little Mattel doll, right? It's Barbie. It's a little doll. Yay. Right? A doll. And what we'd do is we put a little rubber band around Barbie's legs, and we would attach it to a finger, really. So somebody would have their finger standing right here, whoop, and then the rest of their hands would be here, right? Thumb. You get the point. I'm not a great artist. And we would let Barbie fall. Whoa. Let's undo that. Let's let Barbie fall, right? So then what we're trying to really do is see how far does Barbie fall with each. So it took, the group you'd have measured out here, and we would measure this thing in inches, like how far she falls with rubber bands, right? So that's what we're trying to try to figure out here. Now we had a single band or a single string attached right here. So the first one that you see is 12. So because it's a 12-inch string. So she fell 12 inches with no rubber band at all. And then what we'd do is we would just continue to attach a new rubber band, right? A new rubber band, and then another rubber band, and then a rubber band, another rubber band, and then there was this long string, and then there was the doll, right? So that's kind of what happens. Okay, enough on the explanation. Let's just get right to what we're trying to do here. Okay, let's look at topic number 1, scatter plot. It is a display of two quantitative variables. Scatter plot. A display of two quantitative variables. So the way it's going to look is it's going to have like an XY axis. And what we need to do is figure out what we call the explanatory versus the response variable. So we need explanatory versus response variable. The explanatory is the variable, right? There's variable 1 and there's variable 2. It's the variable we believe explains the response, which is the outcome, right? Sometimes distributions have a very clear explanatory and a very clear response. Sometimes they don't. But if we can figure out the explanatory, the variable we believe explains the outcome, and the response would be the outcome, then we're going to put this on the x-axis. So if you want to, you can think explanatory goes on the x-axis, explanatory x-axis. And then the response will go on the y-axis. Okay? So that's what we're going to do. So I want you to come up here, and I want you to look at this data set and say, do I believe the number of rubber bands would explain the distance traveled for Barbie? Or do I believe the distance traveled would explain the number of rubber bands, right? And sometimes it's kind of a hard thing to think about. But what we're going to say is that the number of rubber bands here, I believe that explains the distance traveled. So I'm going to call this, well, let's go this, the explanatory, And we're going to call this the response. This is what I believe happens based on the number of rubber bands. So if that's the case, let's just go ahead and let's start. I'm going to start at 0. 0, 1, 2, 3, 4, 5, 6, and 7. We're going to call this number of bands. Okay? And then on the other side, let's just mark those off. I'm going to actually kind of do the little start here, and then we're going to go, let's go 12, and let's go by twos. 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. Okay, 12, 14, 16, 18, 20, 24, or 22, 24, 26, 28, 30. Okay, so that just gives us a good idea of what's going on there. Oh, and we call this distance. Okay, so a scatter plot is two quantitative variables being plotted on the same plot, both with its x and y values. So let's look at the first one here, 0, 12. 0, 12 would go right there. That's what that first 0 bands and went 12. 114, well, that's going to be right there. 217, well, that's going to be about right here. Now, if you actually had a nice graph, you could get this really nicely done. 3 and 18, yeah, it's just a little bit higher. 4 and 22, okay, keep it marking, 5 and 23, all right, just slightly bigger. 6 and 26, it's going to be up here, 20, 22, 24, 26, that's going to be about right there. And 7 and 30, it's going to be about right there. All right, so that is a scatter plot. So every value that you see on the scatter plot here represents a new data point, right? So I could count the number of points and I can see 1, 2, 3, 4, 5, 6, 7, 8, right? There's 8 in this data set. N equals 8 on this, okay? So there's a scatter plot. That's how you draw it. Real basic. Make sure you're labeling the sides. Try to figure out which one we believe is explanatory, which one we think is response. Okay, here's what we got to do after we do that, just like we did in chapter 1, where after we drew our histogram, we needed to do the SOCs. Now we want to do the same thing here, only we don't call it SOCs. When we describe, we want to do FODS. Maybe there's a better acronym than FODS. Maybe DOFS or SOVD. Anyway, I'm going to call it FODS, all right? Here's what we're looking for on your scatter plot. FODS is your description. So F for form, O for outliers, D for direction, and S is strength. Okay, form, outliers, direction, strength. Let's get into it. Form, we're going to have, in the form, you're either going to have, number 1, linear, and it can be rough linear, but is it kind of linear? Or we're going to have nonlinear. Let's just categorize it into one of those two forms. Outliers, what we're going to be looking for is deviations away from the form pattern. Okay, so if you call the form linear, well, anything that is well beyond that linear, because since most of the values are linear, but a few of them like to stray out of there, yeah, we're going to call them outliers. So that's outliers. Direction. I want you to have one of the three directions. It's either going to be positive direction, it's going to be negative direction, or it's going to be no direction. Okay? Fair enough. Let's do that. And then strength. We're going to be on a rating scale of anywhere from weak. So thinking about your form, how tightly packed are they? From weak on a sliding scale up to strong. So maybe kind of in the middle, we'll call it moderate. Okay, so that's what we're trying to find. So let's look at this one that I got going up here. Back to our scatter plot. So form. So if I were to be able to like put barriers around the outside, can I make a really nice straight line? If so, we'll call it linear. If I had a data set, look in the bottom left of the screen here. If I had a data set, let's just say it looks like this. This would be a clearly non-linear because, right, that definitely looks like it has a nice sharp curve to it. Other nonlinear might be, you know, just scattered all over the place, right? Just like I can't even figure out if that has form or not, and I'm going to call that nonlinear. So linear or nonlinear. All right, deviations away from the pattern. So going back up to our original scatter plot up here, I don't see any deviations because I think my pattern is nice and tight. Now let's just say, I'm going to add a green dot in here. Let's say I had a point right here. Everything else is looking good, but that one green dot, it's definitely out of the normal pattern. That would probably be identified as a possible outlier. And so we'd want to take note of that. Okay, possible outlier there, if we had one. So outliers in this set, I'm going to say no. No outliers in my basic scatter plot up here. Okay, direction, positive, negative, or none. So think about algebra, when you put a line of best fit, thinking slope. So positive slopes, let's go back down here. Positive slopes are going to be like this. Negative slopes are going to be like this. And no slope would be like this. So if, let me undo those. So if I is given this junk of data right here that you're looking at, all in black here, and I would have put a line of best fit, it's going to have to go like this, and we're going to call it no direction. Okay, but let's say we didn't quite have this many points over here. It was far fewer than this, right? Let me think about, like, if I were doing let's say my points look like this. Okay. And then so I came in here just like I did earlier, and I'm like, I'm going to surround it, and I kind of put some barriers on it. That looks pretty linear all of a sudden, and it's moving in a positive direction, upward from left to right. If it looks like it's falling, it's going to be negative direction, and then or no direction. So let's go back up to this one. That's definitely a positive direction, right? So it is moving in a positive direction. That's what we're going to call it. And then finally, strength. And this is how tight my points are to the form that I'm giving it. So on this one right here, back up here, these are all fairly good linear kind of pattern, right? Because I called it linear, and they kind of be matching that linear pattern. So I'm going to say this is close to strong. I could call it fairly strong. I'm going to kind of put it on the scale about right here. So what would we call that? Fairly strong? Kind of strong? Shoot, I'll just use the word strong. I feel like it's strong data set. So that's what that is right there. And those are our FODs, form, outlier, direction, strength. If they ask us to describe, which they usually will once you build the scatter plot, then we need to talk about the FODs. Okay, so then one last piece on this then is sometimes we get an R value. So what an R value is, R value, it's called the correlation coefficient. The correlation coefficient. So it's going to kind of help us with part of our association on this. Here's what it's going to do. It's going to give us a better understanding on how strong a data set is, but also it's going to give us an understanding on the direction. So the R value, here's what you need to know first though. R values only make sense on linear data sets. Okay, so they only make sense on linear data sets. So don't try to use the R value on a curved data set. Just, it's no bueno. Okay, so R value looks like this. So R values can take on a lot of different numbers, but they have to be between. So an R value will always be less than or equal to 1, and it will always be greater than or equal to -1. So let me give you a couple things to know. An R value of equal to 1 is a perfect linear, strong, positive set. Okay? So what that would look like on a data set, let's just say we had that, it would have points that are moving in a positive direction, and they would all fit exactly on a straight line. So if I were to put a straight line, the straight line would touch every single value. That would be an R equals 1. All right, so let's do an R equals -1. That is going to be a perfect, linear, strong, negative set. Okay, so that would be this, right? So it's just going to be going in a negative direction. It doesn't matter how sharp of a negative or positive. That's the R value doesn't tell you that. But then, yep, I could set a line and it would touch every single point. That would be a -1. It would be moving in a negative direction. So the other extreme is R equals 0. This would be no linear. It was going to be as weak as the data set can get, and it has a no direction. Okay, so what might that look like as a data set? If I had values here, it would be like just all over the place, right? So that it doesn't look like, if I put a straight line in there, right, the only straight line I could put would just be a completely horizontal line. It would look like that. That would be an R value of 0. Okay, so now there's variations. The closer you get to +1, the tighter those values get in a linear pattern, but moving positive direction. The closer you get to -1, the tighter they get moving in a negative direction. And the closer you are to 0, the weaker your distribution is, right? So if they said, oh, well, here's a data set. Let's say my data set kind of looked like this right here, right? So think about, okay, direction, I like it. It looks like it's going in a positive direction. I'm going to call that very much linear. I don't really see many outliers. But then let's say I did this calculation and it said, oh, you know what? R is equal to 0.87. Okay, let's just say that's what it said. So 0.87, since this is a positive number, that means my direction should be positive. It matches. That looks good. And since this is getting really close to +1, I'm saying this is a really tight linear pattern. Now, if I drew a straight line through it, right, it's not going to touch every single value. So it's definitely not equal to 1, but it's getting close. Like all those values are really close to one another. So this is helping support part of my FODs, right? It helps support the direction part of FODs, and it helps support the strength part of FODs, right? This is strong because it's 0.87 getting close to 1. It's positive direction. What it doesn't support is outliers or form. So outliers or form, how you figure out form and outliers is you use your eyes and take a look at the graph. That's how you do form and outliers, right? So that's what you need to know for 3.1 statistics using our Barbie Bungee data set right here. The number of bands distribution. I want you to be able to build a scatter plot, describe using FODs, and then go ahead and take an R value and let that also help confirm your direction and strength on that. So we'll get into the next section where we actually put this stuff through a calculator and make it make sense to us. All right. That's all for now.